Session of OOPSLA papers. I'm delighted to introduce the first paper, Stuttering for Free, by Minki Cho, Youngju Song, Dongjae Lee, Lennard Gäher, and Dreyer. And Youngju Song will be giving the talk.
Can you hear me?
Yes.
Oh, great. Thank you. I'm Youngju Song, and today I'm going to talk about freely-stuttering simulation, which we believe is an ultimate form of stuttering simulation. This is a joint work with Minki Cho, Dongjae Lee, Lennard Gäher, and Dreyer. Behavioral refinement, shortly refinement, is a widely used notion in formal verification for relating two transition systems. The target system behaviorally refines the source system if the set of behaviors of the target is a subset of the set of behaviors of the source. In other words, refinement ensures that the target behaves as specified by the source. For example, the correctness of a compiler is usually stated as a refinement between the source program and the compiled target program. One of the most common tools for proving refinements is the method of simulations, especially those more advanced versions of simulations called stuttering simulations. In this work, we propose a new stuttering simulation called freely-stuttering simulation, or FreeSim for short, that provides strictly better usability than all existing stuttering simulations. To see what FreeSim is, let us go step by step. I'll first explain refinement, stuttering simulation, and then explain FreeSim. Consider proving the refinement between the following two systems. In this talk, the state A is always the initial state. On the left is a target system where it either steps to the state B while emitting an event 0 and then comes back to the state A, or it emits an event 1 and directly returns to A. On the right is a source system similar to the target. It either steps to the state B while emitting 0 or steps to C while emitting 1. On both cases, it can return to A, and in case of C, it can step to B while emitting 42. Of course, one could establish the refinement by directly computing the set of all possible behaviors in both systems, and then by giving a mapping from the target set into the source set, and thereby showing the set inclusion. But such a reasoning is temporally global in the sense that we should match a whole trace in the target with a whole trace in the source. With simulation technique, we can prove this in a more temporally local fashion, that we match a step in the target with a step in the source. Now let us see how stuttering simulation can help us proving this refinement. Let us first consider only the subsystem of the previous example. The simulation technique first requires us to specify a relation R, often called a simulation relation. Such a relation should relate the entry point of the target system and the source system. Then one should prove that for any pair of state t, s in R, if target takes a step to t prime, emitting an event E, the source should simulate this behavior by stepping to s prime, emitting the same event. The resulting state t prime, s prime should again be in the relation R. Now, back to the example, we first set up the following simulation relation, which simply relates the corresponding states. Then the proof proceeds as follows. It begins execution on A on both sides, and for whatever execution target takes, the source should follow it, and result in R again. Then for whatever next step the target takes, the source should again follow it, and result in R again. That's all. What we have shown is sufficient to imply refinement because any whole trace in the target can find its matching whole trace in the source by repeating this stepwise translation. Now let us consider the full example. Proving this branch is similar to proving the other branch before, but there is one critical difference. On the target, it takes a single step to get back to A, and on the source, it takes 2 steps to get back to A. Thus, both rule alone is not enough to relate these executions because we can only match the same number of steps. So let us enlarge the simulation with 2 more rules that allows us to execute the source only or the target only. In these 2 rules, only one side is taking a step, which is often called a stuttering step. And this is the reason why such a simulation is called a stuttering simulation. Now let us see how this works with the example before. If target executes the lower branch, we use both rules and pick the upper branch in the source. Now we are left with proving that the target execution can come back to the state A alone. We proceed with source-only rule, in other words, execute a stuttering step in the source. Then the proof is done. As you can see, stuttering simulation provides powerful mechanisms to establish refinement in a local fashion. However, there is one minor caveat. The caveat is that the simulation that I just showed you is actually unsound. In other words, it does not imply refinement. The reason is as follows. Those two edit stuttering rules are overly powerful that it trivially relates diverging system with any other system. For instance, suppose we have a diverging system on the target. We can prove simulation against any system on the source by picking the simulation relation containing just AT and AS, and then, given any t, s in R, we can trivially finish the whole proof by just executing target only. The lesson here is that infinite stuttering is bad. Thus, to prevent infinite stuttering from happening, all the stuttering simulations enforce one more condition to the user. The exact style on how such an enforcement is made differs by simulation, but on the bottom line, they all require the stuttering steps to appear only finitely many times before executing both. With this fixed simulation, it is easy to see that the previous wrong proof is properly ruled out. The wrong proof applied target-only rule infinitely many times without applying both at all. However, while this condition ensures soundness, it is often burdensome to the user and rejects some perfectly valid proof strategy. To see this, consider the following motivating example. Transition systems are now equipped with variables p and q, and assigning a value to a variable is considered a silent event. The system on the left first picks the value of the variable p, either 1 or 0, and then picks the value of the variable q in the same way. After assigning these variables, the system either repeats this process or prints the current value of p and q and terminates in c. So the whole behavior of this system comprises divergence and printing a pair of integers. Now consider the system on the source. It is basically the same as the target, except that it picks the variables in a different order. That is, it picks q first and then p. Now, when proving a simulation between these two systems, existing simulations unnecessarily restrict the proof strategy. Intuitively, the proof should be rather straightforward. Whatever pair of values target chooses, source should be able to simulate it just easily. Specifically, starting from the simulation relation that relates A on both sides, you would like to execute the target twice and execute the source twice, picking the same branches as the target. However, this proof does not work. In the case of a diverging execution, concatenating this proof segment infinitely many times would result in a proof with infinite stuttering steps without executing the both rule. This is somewhat unfair because this is actually a sound proof strategy, unlike the unsound proof earlier. What actually matters for soundness is ensuring that both sides are taking a step, and in this proof, we actually do. Because this intuitive proof fails, all the existing simulations enforces us to find the right place to execute both rules in the foresight. And this is often burdensome. Suppose we just apply both rules in the beginning. However, we do not yet know what is the right branch to execute in the source, and let us just assign 0 to q. But if later the target execution chooses a different path that it assigns 1 to q, it could end up printing a different value on the source and the target, thus failing the proof. Indeed, the only way to conclude this proof is to execute target only, both, and source only in this exact order. To summarize, in existing simulations, the user needs to understand the system in detail before starting the verification in order to execute the both rule at the just right point. This enforcement complicates the proof, and here comes our question. Can we verify this example asynchronously as in our first attempt? The answer is yes. And the key idea of FreeSim could be pictorially described as follows. To begin with, progress is what ensures the soundness of a simulation technique, where progress means that every proof segment, a proof starting from R until it comes back to R, contains at least a step on both sides. What existing simulations enforce is what we call a synchronous progress, meaning that it should execute the both rule. However, the synchronous progress is just one way to ensure progress. In FreeSim, we relax such a condition and allow what we call the asynchronous progress. In FreeSim, executing any stuttering step now contributes a partial progress on each side. Source only contributes the source partial progress, and target only the target partial progress. These partial progresses can be made asynchronously, of course, and later be combined into a full progress. And the asynchronous progress interface gives us strictly better usability than the synchronous progress. This is because every proof involving the synchronous progress can be translated into a proof with the asynchronous progress. This is the summary of our contributions. We developed FreeSim that allows asynchronous progress for the first time. FreeSim is propositionally equivalent to existing simulations, but it offers a strictly better usability than all existing stuttering simulations that we know of. To objectively compare the usability of these different techniques, we have devised an interesting notion called replayability. Our theory is fully formalized in Coq, and we evaluate FreeSim through various challenging case studies, including extending ITrees library with dual non-terminism. FreeSim is ready to use and is available in OPAM. In the rest of the talk, I will explain the upper 2 points further. The definition of the FreeSim is as follows. For any pair of state in R, one should proceed the proof with K, which is inductively defined with 4 cases. The relation K carries 2 Boolean flags, BT and BS, each denoting whether partial progress has been made on the side. Executing both rules turns on both flags, and executing the stuttering steps turns on only the corresponding flag. When concluding the proof with the base rule, it checks whether the full progress has been made. Now let us consider the motivating example before. It begins the proof with the both flags as bottom. Turn the target flag on when executing the target. Turn the source flag on when executing the source. And we can now conclude the proof since both flags are on. So we have seen what FreeSim is, and there is one last thing I would like to talk about today. At the beginning of the talk, I bragged about FreeSim being an ultimate stuttering simulation, like the only stuttering simulation. And I'll explain why I think so. FreeSim and existing stuttering simulations, notably explicit stuttering simulation and implicit stuttering simulation, are propositionally equivalent. It means that if one simulation can relate 2 systems, the others also can somehow relate those systems. However, as we have seen before, FreeSim offers more proof strategies and giving a better usability. Such a difference is captured with the notion that we adopt replayability. FreeSim can replay the other 2 techniques, but not vice versa. Okay, so what is the replayability, and why should we care about that? Replayability is defined as follows. If a host technique can replay the guest technique, it means that the host can do everything guest can do. In other words, the host technique can emulate the behavior of the guest technique. Formally, replayability means that for whatever rule the guest applies, the host can simulate it with its own rules. What is even more interesting with replayability is that it gives free techniques. If a host technique can replay 2 different guest techniques, 1 and 2, it can mix these 2 guest techniques in a single proof. For a specific subproof, it may use the technique 1, and for the rest, it may use the technique 2. This gives rise to a free technique, 1 plus 2, that allows interleaving between these 2 techniques. So in this slide, I have put all the stuttering simulations that we know of, a zoo of stuttering simulations. As mentioned, FreeSim can replay eSim and iSim. And on the top, there are 3 additional variants of stuttering simulations called MSim, FSim, and EFSim, used in the context of CompCert. We have proven that FreeSim can replay FSim, and then FreeSim replaces the remaining 2 for free. This is because MSim is a mixture of eSim and FSim, and EFSim is a mixture of FSim and iSim. Note that these techniques were proven manually before. All in all, FreeSim can replay all the stuttering simulations that we know of. In the paper, there are other interesting points that I wasn't able to cover today. While I have sanitized all the serious advanced mathematics in the presentation, this work actually required a good amount of them. And we generalized FreeSim further that Boolean flags are extended to ordinal numbers. We show that FreeSim scales better when adding new primitives like angelic non-terminism, and also provide a compositional rule stronger than before. I'm on the job market this year, and Dongjae Lee is applying for PhD. Thanks for listening, and I'm happy to answer any question.
All right, we have time for a couple of questions. Let me start things off. First of all, really enjoyed the talk. It's nice to see this very general technique. I wonder if any of your case studies illustrate what you talked about in terms of replaying other proof techniques or maybe mixing different proof techniques.
Yes, like the one major case study in the paper is about replaying the proof techniques in CompCert. CompCert comprises multiple different simulation techniques, like each opted in for like specific purposes. And what we realized is that the FreeSim can be like a unifying foundation for all these different stuttering simulations. We can replay like all the stuttering simulations in CompCert, basically.
Excellent.
Yeah.
So another thing question I had about your technique is you mentioned that you can use ordinals as flags in addition to booleans to see to track the correspondence between making sure both sides take steps. What benefit do ordinals give you for the theorem prover versus booleans?
That's actually a very good question. So when replaying the explicit stuttering simulation techniques, by which I mean the stuttering simulation techniques already equipped with ordinal numbers, like we need to extend the boolean into the ordinal numbers, and having such a fine-grained flex is useful when you are proving optimizations in compiler, because it gives you more dimension on specifying your simulation relations. So for instance, the simulation relation the CompCert uses already uses this index varying from the natural numbers or pair of natural numbers, or they don't use ordinal, but yeah, they already use such a power. Yeah.
Excellent. And one last question. So you mentioned usability, and I can sort of intuitively see the benefits for usability in the flexibility of the proofs. But I wonder, might it be possible to take this and do a user study to show that people can prove more easily using your technique?
That will be a very interesting the future work. It isn't included in this paper, but yeah, that will be definitely very interesting. Yeah.
All right. Any other questions? Well, let's go ahead and thank our speaker. Thank you so much.